Welcome to the first presentation in Unit 4 entitled Opposites Attract. This is in science, one tries to tell people in such a way as to be understood by everyone, something that no one ever knew before. But in poetry, it's the exact opposite. Paul Dirac. So the learning goals for this particular presentation are that students describe the formation of ions as electrons are transferred between atoms, that they distinguish between cations and anions, and that they describe the properties of ionic bonds. So first, here's what we already know. We already know that chemists are interested in the valence electron structure of atoms because it's the valence electron structure that determines the reactivity. That's what we talked about at the end of Unit 3. So the valence electrons are represented by dots around the chemical symbols. Now you should know that these are incorrect representations of the Lewis dot structures. Remember, you always have to put the first two electrons together. Now the reason why we draw it this way is because we want to point out the mistake that this is. A lot of people want to draw the electrons as far away as possible, but the first two have to go together. So nitrogen and lithium are the only ones that are actually correct Lewis dot structures. Now atoms can attract to each other to form new compounds. So here's what we learned in the lab. Positive charges will repel other positive charges. Positive charges will attract negative charges, and negative charges will repel other negative charges. So the octet rule. Atoms are most stable with 8 valence electrons on it. That's why we draw the Lewis structures when we say, okay, neon, 1, 2, 3, 4, 5, 6, 7, 8. That is a stable structure because it satisfies the octet rule. 8 valence electrons caused atoms to act like noble gases. So if you were to look at sodium, if it loses an electron, will satisfy the octet rule. It will have 2, 4, 6, 8 electrons in its valence shell if it can get rid of that one. Fluorine, on the other hand, has 2, 4, 6, 7. So if it can gain one electron, it will be stable. So if sodium somehow transferred its electron to fluorine, both would have 8 electrons in its valence shell. Okay, the problem is if the electrons are transferred, sodium becomes positively charged because it loses an electron. Fluorine becomes negatively charged because it gains an electron. So, just as a refresher, the noble gas, group 18, noble gases satisfy the octet rule. Because of that, 0 electrons are transferred for noble gases. As a result, they always have 0 charge and they have essentially 0 reactivity. Okay, so the whole reason is everything wants to satisfy that octet rule. Alkali metals have 1 valence electron to begin with. So what they can do is they can lose 1 electron. Whenever they lose an electron, they have a charge of +1. So everything right here is considered to be a charge of +1 in the first column. So first column, column 1, group 1, charge of +1. Next you have group 2. It has 2 valence electrons, so it wants to lose 2 electrons to satisfy the octet rule. As a result of that, everything in group 2 has a charge of +2. So group 2, +2. Now in the middle, we have what are called the transition metals. We don't consider there to be any sort of pattern as far as the valence electrons are concerned. It has something to do with what we call a delocalized d orbital, but that's well beyond the scope of this class. So because of the d orbital, there's no consistent pattern of charges. Instead, what we do is we specify the charge with Roman numerals. Group 13, which is over here, also has 3 valence electrons. As a result of that, it can lose 3 electrons, and it has a charge of +3. So if you notice, 13 and 3. So that allows us to skip these 3 through 12, and we still have a consistent pattern of 13 and 3. So that means we get to group 14. Group 14 has 4 valence electrons. Whenever you have 4 valence electrons, something like carbon, it is just as easy to gain 4 electrons as it is to lose 4 electrons. As a result of that, carbon can become a plus or a -4 depending on what it bonds with. That's actually what gives carbon some very unique properties and is the reason why life is based around carbon. Carbon has the ability to form the most number of bonds in the most number of ways based on the fact that it can gain or lose electrons. Group 15 has 5 valence electrons. At this point, when you have 5 valence electrons, it's easier for you to start gaining electrons. Whenever you gain electrons at this point, you become negative. So if it gains 3 more electrons, then it will satisfy the octet rule, and at that point it has a charge of -3. So at this point, the pattern kind of breaks down. You have 15 and then -3. Then we go to 16. 16 has 6 valence electrons. When it has 6 valence electrons, it's much easier for it to gain 2 than it is for it to lose 6. So because of that, it can gain 2 electrons and has a charge of -2. The halogens, which is this last reactive column right here, has 7 valence electrons. Whenever it has 7 valence electrons, it is much easier for it to gain 1 electron than it is for it to lose 7. So because of that, the halogens have a charge of -1. Okay, so if you think about it this way, you have +1, +2, +3, plus or -4, -3, -2, -1, 0. So if you can just kind of start off with +1 and 0 and kind of find a way to work your way into the middle, 1, 2, 3, 4, 3, 2, 1, 0. Okay, now this right here we skip because there are variable charges. That's why we have to specify them with a Roman numeral like 1 or 3 or 4. Cations. Cations are very specific ions that have a positive charge. They are group 1 through 1, 2, and group 13, and are more stable with less electrons. So this right here is an example of a lithium ion, okay, because it has 1, 2, 3 electrons. It's not a lithium ion, it's a lithium atom. Lithium is much more stable if I remove this electron because at this point it has a full octet, or it has a full shell. Now, this is where it becomes very, very important that you kind of think about it. Helium is stable with 2 electrons because it's in that first column. So lithium can be stable with 2 electrons as well. It's one of the exceptions to the octet rule, but the only exceptions to the octet rule we're going to talk about are helium, hydrogen, beryllium, and lithium. Everything else is going to satisfy the octet rule. These are stable with 2 electrons. Anions are group 15, 16, and 17 and are more stable with more electrons. So if you were to look, you have 1, 2, 3, 4, 5 valence electrons right there. This right here would be an example of nitrogen. So nitrogen is not particularly stable because it doesn't have enough electrons. This right here is oxygen. It has 6 electrons and it's not particularly stable. But if I were to add 2 electrons to it, it would have 8 in its valence shell. If I were to add 3 electrons to it, it would be stable with its valence shell. With fluorine, fluorine is more stable as F- than it is as F. Nitrogen is more stable as N3-. Oxygen is more stable as O2-. So match the group number with the appropriate charge for a stable ion. So group 2, remember group 2 has a positive +2 charge because it's easier for group 2 to lose its electrons. Group 18. Group 18 is the noble gases. They have a charge of 0. Group 16 is a charge of -2. Group 14 can go to plus or -4, and group 9 is in the middle of that 3 to 12. It's a transition metal, so because of that there is no stable pattern. How many valence electrons does a stable sulfur anion have? So at this point, remember we have sulfur, and sulfur normally is in group 16, so it has this. This is not stable. The reason why is it doesn't satisfy the octet rule. So in order to satisfy the octet rule, it has to gain 2 more electrons. When it gains 2 more electrons, it now has 8 valence electrons, and we can actually write it as S2- because we've added 2 electrons and each one of those electrons is negatively charged. How many of each does a stable nitrogen 14 ion have? So we have a stable nitrogen 14. Remember, this indicates the atomic mass. Okay, so if we're looking at it, the first thing we can say is, well, all nitrogens have 7 protons because of their atomic number. Because they have 7 protons and their mass has to be 14, I can say 14 minus 7, and I can say that I have 7 neutrons. The next thing that I need to decide on is that it's a stable nitrogen ion. Okay, so because it's a stable nitrogen ion, this is normally what nitrogen is. Okay, because it's in group 15, it has 5 valence electrons. It needs to add 1, 2, 3 electrons in order to become stable. So when we say stable, it means it has 3 extra negative charges. So when we talk about the total number of electrons, remember nitrogen should have 7 because normally protons and electrons cancel out. But because I have 3 extra electrons, now I have 10 total electrons. And I have 8 in the stable. In order to be stable, I have 8 valence electrons. Next it says carbon can have a positive or negative charge. Describe what atoms carbon can interact with, resulting in a positive charge and resulting in a negative charge. So the easiest way to do is to look at it in this perspective. Lithium has 1 electron that it wants to get rid of. So it would very much like to give its electron to anything. If there's a carbon around, it will donate its electron to carbon. So if lithium somehow bonds with carbon, then that means that the lithium would be the positive and the carbon would be the negative. So if carbon bonds with something to the left of it, carbon becomes negative. Now if carbon wants to be positive, what it would do is it would bond with something to the right of it. Something like oxygen. Oxygen only needs 2 electrons because it has 6 valence electrons to begin with. Carbon can take or lose electrons, so because of that, it can easily give these 2 electrons to oxygen. So if carbon forms a bond with something to the right, it will be positive. If carbon forms a bond with something to the left, it will be negative. So what we now have is we have something that's called an ionic bond. An ionic bond is the attraction between a positive and a negative charge. It's governed by something called Coulomb's law. And Coulomb's law basically says that opposites attract and like charges repel. There's a formula for it that you may get into in future classes, but for now, opposites attract and like charges repel. And it's actually a very, very strong attraction. So when you have a positive charge and a negative charge, they attract each other very, very much. So this is really hard to pull apart. So the charge and ionic bond. Ionic compounds are neutral. Okay, so whenever you have an ionic compound, you have like a sodium and a chlorine. Those two things together, if you look, they're neutral. The positive and the negative cancel each other out. If you have something that looks like this is not an ionic compound because the charges do not balance out. You have 1 positive charge and 2 negative charges. Now the way that you can actually get it to balance out is you put another sodium there. And so you'd have something like Na2O. So the charge has to balance out an ionic bond. It has to be neutral. Now the strength of the ionic bond. Remember we talked about the positive and the negative charge being very much attracted to each other. Since they are very much attracted to each other, it is an extremely strong bond. It is very difficult to take a solid sodium crystal and heat it up where these two things separate. It requires a large amount of energy. So the ionic bond is actually considered to be the strongest bond that we have. Okay, the ionic bond always forms between a metal like sodium and a nonmetal like fluorine. It's never going to form between 2 nonmetals or 2 metals. It's always 1 metal and 1 nonmetal. Now, the greater the charge, the stronger the bond. So right here you have sodium chloride. You have a charge of +1 and you have a charge of -1, and those are attracted to each other with a big, big attraction. But whenever you have barium right here and sulfide, you have a charge of +2 and a charge of -2. Because the charge is greater, the attraction between the two is greater as well. So the greater the charge difference, so if +2 and -2, the greater the strength of the bond. Now, this can affect the state of matter. Whenever you have an ionic compound, it is always a solid at room temperature. And the reason being, it is very difficult to separate those positive and negative charges. In order for it to become a liquid or a gas, it's got to have free movement. These things have to be able to move relative to one another. And they can't because of what the strength of the attraction is here. So because of that, it requires a large amount of energy in order to change the phase. In fact, most most ionic compounds won't liquefy, they won't turn into a liquid until you get to over 1,000 degrees Celsius. Okay, the solubility in water. The majority of ionic compounds dissolve in water, and the reason why is water has an H, an O, and an H. And the H's have positive charges, and the O has negative charge. So because of that, they can arrange themselves where the sodium goes to the negative and the chlorine goes to the H. So you have this separation of the ion based on the fact that it can attract to another charge. So whenever you have something, this is generally called like dissolves like. If you have a positive charge and a negative charge, if you want to dissolve something that has a positive charge and negative charge, they will dissolve in each other. Okay, they're generally brittle. Ionic compounds form crystals that are brittle, and the reason why is there's no difference between an attraction between these two and an attraction between these two. If you were to kind of push these things, it easily shatters the crystal. If you move it over just a little bit, it will cause shear stress, which will cause it to shift. Whenever it shifts, it'll go ahead and fracture the crystal. So even though the attraction is very strong, just a little fracture can actually cause it to shatter. So circle the properties that describe the ionic compounds at room temperature. The first one that we know is because it's at room temperature, we know it's going to be a solid. Okay, we know that it's going to be brittle. It's going to fall apart very easily. We know that it's not malleable. Malleable means if you hit it with a hammer, it will pound out into thin sheets. If you hit this with a hammer, it'll shatter. We know they're not liquids at room temperature. We know they're not gases at room temperature because of the strength of the bond. We know that they do have a strong bond, so it's not a weak bond. We do know they are soluble in water for the most part. And at this point, they're ionic, so they're crystals. They tend to not be lustrous. Lustrous is shiny, so they don't quite have that shininess that they do as metals by themselves. Now, which of the following is the most difficult to break? Now, remember, in terms of most difficult to break, we're looking at the charge. So we look at sodium and chlorine. We look at sodium, and it says it's in the group 1, and this is group 17. So we have a +1 and a -1. So that's a strong attraction. But it's not as strong as calcium and oxygen. Calcium's in group 2, and oxygen's in group 16. So because of that, calcium and oxygen have a +2 and a -2. That attraction is much stronger than the +1 and the -1, so we can cross through that. The last one is aluminum and nitrogen. Aluminum is in group 13 and nitrogen is in group 15. Because of that, aluminum is +3, nitrogen is -3. That is going to be the strongest attraction of all of them. So if you had to rank them in terms of strength, this one is going to be the strongest because of the +3, -3. Then you have calcium and oxygen, which is next because of +2, -2. Then finally you have sodium and chlorine, which is last. It's still very strong, it's just not as strong as aluminum and nitrogen. It says identify the ionic compounds using the information below. So what we have right here is we have the melting points. Now the melting points are you expect to be very, very high for ionic compounds. And if you look, you see this right here is clearly an ionic compound. It has a very, very high melting point. This additionally is a very high melting point. So because of that, we can say right away that those are ionic compounds. You can also identify this as an ionic compound, but the reason why this one is much lower, than these two actually, is because they involve something called a polyatomic ion. Whenever you have a polyatomic ion, it has some covalent bonds, which we'll get to, and so therefore it artificially lowers the melting point. These are the ones that only involve ions. Okay, they only involve a metal and a nonmetal. These involve the bonds of several nonmetals, so that's the reason why it kind of skews it. But the melting point is one of the things that you can look at to see if it's ionic or covalent. It says sodium chloride will readily dissolve in water, but not octane. What does this tell you about the charge distribution in water and octane? We already talked about this real briefly. There's a negative charge by the oxygen, and there's a positive charge by the water. That allows the sodium molecules to kind of separate, where you can have a sodium by the negative and a chlorine by the positive, because opposites attract. What that tells me about gasoline, the fact that sodium chloride will not dissolve in it, is that there is no positive and negative charges. Instead, everything is neutral. Well, since everything is neutral, it makes more sense for the sodium and chloride to stick together than it does to separate.